So today we will have, can you see the screen?
Yeah.
Okay. So today we will have two parts of tutorial question today. We have column buckling and torsion. Okay, the first part is column buckling. Now we have two problems. And if you remember last week, the practical was also related to column buckling. So this will be like practice for what we have done last week. Okay, so this is the first problem. We have a truss or two members like truss, and one horizontal and one inclined, and we have an applied concentrated load B at A, and the cross section of member AC is rectangular section 50 by 100 millimeter, and the requirement is to determine the factor of safety with respect to buckling about y-axis due to the applied loading, and given B is 15 kilonewton, E for steel or Young's modulus for steel is 200 gigapascal, and the yield strength is 360 megapascal. Okay, I will now shift to Ben to start the explanation for this problem. So we have today, first part is column buckling problems. For the first question, we have two members, one horizontal and one vertical, one inclined. And we have an applied force B at A, this is B, and this C. The dimension given, the height of this member is 3 meter. The length of this member is 8 meter. The angle between these two members is 30 degree. Okay, if we have a cut here, the cross section of member AC is rectangular. The width is 100. The height is 50 millimeter. And given that this is the horizontal axis and this is the vertical axis, the vertical axis is XX and the horizontal axis is YY. Okay, the parameter given or the data given, B equal to 15 kilonewton, E for steel is equal to 200,000 megapascal, and sigma yield, the yield strength for this steel is 360 megapascal. Okay, and the requirement is to find the factor of safety with respect to buckling for member about y-axis for member AC. Okay, how can we proceed in this problem? To proceed in this problem, we have 3 steps. The first step is to find the force or the internal force in member AC. So we have to find FAC. The second step, to know if this member will fail due to buckling or this the critical, or we will reach the critical load or not. We need to know the critical load for this column or Euler load. If you remember from last week, the formula for Euler load is pi square EI divided by L effective square. Okay, the third step is to compare these two values together using the factor of safety. the factor of safety equal to the critical load divided by the force in member AC. And we have two cases or two expectation. If factor of safety is greater than 1, this means that the critical load is, or the force in the member is less than the critical load. This means that if AC is less than B critical, this means that the member is safe, or we can say that no buckling will happen in this member. Okay, but if we find that the factor of safety is less than 1, if the factor of safety less than 1, this means that if AC is greater than the critical load, and this means that the member is unsafe because it will buckle, or the buckling will occur. Okay, this is a brief explanation for what we need to do in this problem, or any problem in buckling. We need to find the force in the member and compare or check with the critical load. And we have two cases. If the force is less than the critical load, so no buckling. If the force is greater than the critical load, so the buckling will happen. Okay, so now we return back to our problem. So this is the inclined member. This is the horizontal member we have, and this is the force P, and we know that P is 15 kilonewton. This height is 3 meter, this which is 8 meter. This angle is 30 degree. So the first step is to find the force in member AC and AB. How to find the force in member AC and AB? If you return back to our first tutorial and second tutorial, if we have a truss member, to find the force in the members, we need to cut. And if we cut, we will have the internal force. If this member, this A and this B and this C, so the force in this member is FAB, and the force in this member FAC. So when we make this cut, we will find or know the direction of the force. And we assume the force in this direction because this is the tension direction. I just remind you that if we have this member applied to tension, so the internal forces will be in this direction, and we call this tension. If the forces is pulling the member, so this member is under compression. So I assume tension because this is a positive sign. To find the forces, we need to study the joint A. So at joint A, just extract the joint. We have the applied force B equal to 15 kilonewton, and here is FAC, and here is FAB, and the angle is 30 degree. Okay, so to find the forces, first we need to subdivide the force or divide the force AB because it is inclined, so we have two components. If this 30, so this will be 30. So the horizontal will be FAB cosine 30, and the vertical will be FAB sine 30. Okay, so if we apply summation Fy equal to 0, so we have FAB sine 30 acting upward minus 15 acting downward should be 0. This gives us FAB equal to 30 kilonewton, positive. What does the positive sign mean for us? The positive sign means our assumption is right. So right. And yeah, and the force is tension, not compression. Okay. And now we can shift to the horizontal force or horizontal equation. Summation fx equal to 0. So we have FAB cosine FAC. So FAB cosine 30 plus, because this acting to the right, and plus FAC equal to 0, also acting to the right. We already know that FAB is 30. So from this equation, we will find that FAC will be negative 25.98 kilonewton. What does the sign mean for us? What does the negative sign mean for us? That our assumption, the assumption was not correct, and the force will be compression, not tension. Okay, so if we want to put the forces, the final result. So this force is tension, 30 kilonewton. This force is compression, 25.8998 kilonewton, and we have 15 kilonewton here. Okay. Do you have any problem in this first step? This is a step from the beginning of our course. Okay, so now we have tension in member AB and compression in member AC. Okay, tension, this member AB is under tension. If the member under tension, this means that no possibility for buckling to occur here. That's why he didn't ask. The question didn't ask for the buckling of member AB. So member AB under tension, so no buckling. But here, because this member is under compression, member AC, so there is a possibility of buckling to happen in member AC. So we need to check buckling. Okay, so if this is a general question without, if he didn't like assign what member he need to to find the buckling factor or the factor of safety for buckling, so no possibility to find this factor for AB because it is under tension, only for AC because it is under compression. Okay, so now we shift to the second step. The second step will be the critical load or Euler load. Again, the formula for Euler load by square E I divided by L effective square. So returning back to member CD or AC, sorry, this member AC. We have here, this is the force in the member, FAC equal to 25.89 kilonewton. So this is actually the force. And given to you in the question that if we make a cut here, this is the cross section for the member, 50 millimeter and 100 millimeter. And this is the axis. This is X axis and this is Y axis. Okay. If we return back to the question, he asked you for the factor of safety of buckling about X axis or Y axis? Y axis. If we asking for the buckling about Y axis, so I in this formula is IX or IY? IY, because the buckling will happen about Y. Okay, for your information, the buckling is critical about the minor axis, not the major axis. So if you have this cross section, what is the major axis and what is the minor axis? X axis is the major axis, and Y is the minor axis. Minor and major because IX will be greater than Iy. So X is major and Y is minor. So buckling is critical about major or minor?
Minor.
Minor. So if the buckling will occur, so it will happen first in the minor, around the minor axis, not around the major axis. Okay. So to find the B critical, we need to find this three parameter given for us E equal to 200,000 MBA. I, Y. How can we find IY? If this Y, so IY will be the parallel to X, so to Y, which is 100, multiplied by the normal to X, which is the normal to Y, sorry, which is 50 to the power 3 divided by 12. So this will be IY. IY will be, from calculation, will be 1.04166 multiplied by 10 to the power 4 millimeter to the power 4. This will be Y. The last
Have,
parameter, or the third parameter we need to know is L effective. L effective is equal to K multiplied by L. And again, L effective is the effective length for buckling. And we said before, K is buckling factor. And if you remember from last week, K equal to 1, K equal to 0.5, and K equal to 0.7. 1 if the column is bin, 0.5 is the column is fixed, and 0.7 if the column is fixed bin or bin fixed. Do you remember? Okay, hopefully you remember. If we
I'm a,
return back to our,
I have a question.
yeah, okay,
I
go
didn't
ahead.
get why you used I and y axis for calculating the moment.
For the calculating the inertia.
Yep. I didn't get like why usually x axis is on the horizontal side and
Yeah. This is
why
not, yeah. If we return back to the question, you can see the question now.
no
Now
yeah now it's clear. Yep.
I'm just
Oh,
following the question.
okay, got it.
Okay. Normally he both the x-axis is the horizontal and y is the vertical. But if he changes this in the
Yeah,
question, you need to follow the question only.
yep.
Okay.
He just changed the names and that's it. Yep.
Yeah. Because just to make a trick, if you
Yeah,
only yeah.
yep. Got it.
Okay.
Thank you.
No worries. So if we return back here, so our column will be one of these three cases to know what is the value of k. This our member we have bin here and bin here, right? It is appear in the geometry of the question, and also he mentioned this in the question. So if the column is bin, so our k will be 1. So k will be 1. The length of the member, this member is 8 meter, so 8. So the member L effective for this member will be 8 meter. Okay, so now we find the parameter, so we can substitute in the equation. B critical will be pi square multiplied by 200,000 multiplied by IY 1.0416 10 to the power 4 divided by L effective, which is, what is the value of L effective we need to put here?
8.
Eight.
Yeah, but we have a small problem here because 8 here in units of meter,
Meters,
and all this units is in
millimeters,
millimeter. This Newton by millimeter square, this millimeter to the power 4. So if you put 8, the value will be,
thousand.
yeah, far from our correct result. So this need to be converted to millimeter by multiplied it by 1000. So just to be careful when you substitute because of the units. Okay, so this should be 8,000 millimeter. So finally, we get the critical load for this member, which will be 32,127 Newton. In kilonewton will be 32.127 kilonewton. Okay, so this is our second step, finding the Euler load or the critical load. So the third step is to find the factor of safety for this member or for buckling. Before proceeding to the factor of safety, the failure, the failure for this member or compression member may happen under two cases. May happen due to buckling or yielding. Okay, yielding means if we have like cross section or column like this and we apply load. So maybe the stress equal to the force divided by the area is greater than the yield load. This means that this area is not sufficient enough. If the area is not sufficient to carry the load, so the column may fail under yielding. Okay, but if the area is sufficient, so the possibility will be to fail due to buckling. So we need to check that the column will not yield before buckling, because if it yield before buckling, so no meaning for factor of safety for buckling. Okay, how can we do this small check? To do this small check, we will find the stress at critical load or the stress at Euler load. This stress will be equal to the critical load divided by the cross section area. So this is the cross section area. So we know now critical load is 32,127 divided by the area. The area is 50 multiplied by 100. So given to us that sigma yield will be 6.42 MPa. So if we compare sigma critical 6.4 to sigma yield is 36 MPa. Is there a possibility to fail due to yielding in this problem?
No.
No, it's very far from yielding.
Yep.
So
No,
yeah. So
it's failure due to buckling.
yeah. So buckling will happen before yielding. So this is just a small check to check that yielding will not happen. Okay. So now we can find the factor of safety, which will be the critical load B critical divided by FAC. We find that B critical is 32.127 kilonewton divided by 25.98 kilonewton as well. This gives us the factor of safety is 1.23. So do you think the buckling will happen in this problem? Or no? Here, as we said, the factor of safety is greater than 1. If the factor of safety is greater than 1, this means that no buckling will occur. So the column is safe or the member is safe. No buckling will happen. Okay.
Ahmed, where
Yeah.
did you get this formula from? P by F is equals to vector of safety.
This is just like from understanding only. No, this is not a formula. It's just if you
Ratio.
need to, yeah, you need just to check the for anything you need to compare the force or or whatever, force or stress, anything, force
Mm-hmm.
or stress or strain with the allowable stresses or the allowable forces. Okay, if the force of stress is greater than the allowable force or the stress, so this means unsafe or failure. If the force below or lower than the allowable stresses, this means safe. Okay,
Okay,
so
so here PCR is force and F is
yeah,
force as well.
BCR is the allowable
Force.
values or
Yep.
allowable value, and this is the force. Just if we put this formula in or this relation in a shape of formula,
Okay,
we just
so
yeah
yep. So it's just like calculating ratio and then
yeah. If the
uh,
you have many ways to express this.
otherwise we can just say F is greater than the allowable P.
Yeah,
So it's
same idea. That's
good.
just in design factor of safety means like how much you
Extra, I
weaken
think.
yeah or weaken the strength of the material or increase the load to be in the safe side.
Yep, got it.
Okay. Do you have any question in this problem?
No.
Okay. So now we can shift to the next problem. So now we have the second problem in buckling. We have a beam, horizontal beam AB, and a vertical column or brace CD. And this column or this beam, sorry, is uh, is loaded with the uniform load W. Okay, and the requirement is to find the maximum W that can be applied so that the brace or the column CD doesn't buckle. Okay, and this given the properties of this column is 50 in diameter, and the Young's modulus is 200, and the yield strength is 250. Okay, this is the same like the last or the previous problem, but has another idea. The idea is just using the buckling load or the critical buckling load to find the maximum W. Okay, so I will now shift to the bent. So we have question number 2. This is our problem. This D, C, B, A, and we have uniform load W, kilonewton per meter here. The dimension given is column height is 4 meter, and this is 2 meter, 2 meter. Okay, and from the question, if we cut here to see the cross section of this is a circle, circular section. This circular section is 50 millimeter in diameter. Can call this section 1 1. So this is section 1 1. Okay. Also given that we need maximum W, this is a requirement, and given that E for the steel is 200,000 megapascal, and the yield strength of steel is 250 megapascal. Okay. So now how can we find the value of W here? Same procedure like the previous problem. One, we need to find the force in the member CD. So we need to find the force first in CD. Then we need to find the critical buckling load for this member. Okay, and if we equalize these two forces, because this is the maximum load this column can carry, so if we're equalizing these two, so we can get maximum W. So this is briefly the idea to find W. We need to find the force in CD and the Euler load or the critical load for CD, then equalizing these two values together with each other, so we can find W. Okay, so now how can we find the force in member CD? Similar to the previous problem, if we cut in member CD, so we will find that there is a force in member CD if CD. Okay, but I will just, yeah. But what do you expect the direction for this force? Because all the loads are acting downward, so this force should be upward. We don't need to assume it downward, then negative. So from the beginning, we assume it upward, and this will be for F is CD. Okay, and if we deal with this part alone, so we will have F CD, because this member acting as a hinge or roller under the beam. So we just deal with this fraction, this A, C, B, and this is a uniform load W. Okay, and we know now this is 2 meter, 2 meter. Because this also hinge, so we will have a reaction here, Y, A. So we have FCD and YA as unknown. To find these two unknowns, we need to concentrate the distributed load. We will concentrate this part here and this part here. This part will be 2 meter multiplied by W, so 2W. Also this part will be 2W. These two components will act in the middle of two, so 1 meter, 1 meter, here 1 meter, 1 meter. Okay, so now we can find the force in FCD. To find the force in FCD, we can apply the moment equation at A equal to 0. So summation moment at A should be 0. What cause moment at A? 2W, FCD, and 2W. And we know that anti-clockwise is positive sign or positive assumption for us. So we will have 2W multiplied by 3 minus, because it's acting in this direction, minus FCD multiplied by 2 because it is acting in this direction, plus 2W multiplied by 1 because it's acting in this direction should be 0. This gives us FCD will be 4W. Okay, if you want to find YA, summation Fy equal to 0, so FCD minus 2W plus YA should be 0. You know that, or we get that if CD is 4W, so YA will be 0. We don't need YA, so doesn't matter, you don't need to find it. But what we need only to find if CD equal to 4W. Okay, now we shift to the second step. Second step is to find B critical for this member. B critical equal to pi square EI divided by L effective square. Here is our column, this C and D. The height of this member is 4 meter. If we cut in this member, we find that this member is circular. This member is circular with diameter equal 50 millimeter. So E equal to 200 megapascal, 200,000 megapascal. I, what do you think here, Ix or Iy? For circular member, it is symmetric in all directions. So I equal to by d to the power 4 divided by 64. So by 50 to the power 4 divided by 64. This gives us I equal to 30.679 multiplied by 10 to the power 4 millimeter to the power 4. Okay. For L effective, the third parameter equal to K multiplied by L. K in this case 1 or 0.5 or 0.7. Here and here is the two ends. Ben, Ben.
It's 1.
Yeah, so if the column is Ben, this means that K will be 1. So L effective will be 1 multiplied by 4, so 4 meter,
Yeah,
which is equivalent to
4,000.
4,000 millimeter. And now if we return back to this formula, substitute in B critical formula, B critical will be by square multiplied by 200,000 MBA multiplied by 30.679 multiplied 10 to the power 4 divided by 4,000 square give us B critical equal to 37,849 Newton, which is equivalent to 37.849 kilo Newton. Okay, so now we know B critical and the force in member CD. The third step is to find W. To find W, first we need to check that the column will fail due to buckling, not due to yielding. Okay, so we need to find sigma critical in yielding, sigma critical, which is equal to B critical divided by area. B critical just here, so 37,849 Newton divided by area. What is the area for circular section? A will be by d square to the power 4. So by 50 square to divided by 4, this gives us sigma critical equal to 19.276 MBA. So is there any possibility for yielding here?
No.
No, because sigma critical equal to 19, much less than sigma yield equal to 250 MBA. So the final step, just collating the two terms together. So we have if CD should equal to be critical to find maximum W. So if CD is for W equal to be critical, which is 37.849 kilonewton, give us that W will be 9.46 kilonewton per meter.
Just a question.
Yeah, okay.
What would have happened if this might have failed due to yielding?
If this happen, if this failed due to yielding, so do you have any other question here?
No, that's it.
Okay, so just for your question, if this will fail due to yielding, so yielding is dominating. So no, we don't use the critical load here because no meaning for this. So we will have B yielding instead of B critical. Okay. What B yielding? B yielding will be equal to sigma yield multiplied by the area. Sigma yield is 250. The area is by 50 squared divided by 4. Okay. So this will be the value of B yielding. And to find the W or the value of W, so if VCD equal to B yielding, so 4W equal to 250 multiplied by pi 50 squared divided by 4. And you can get W. I will calculate for you. Do you get it?
Yep.
Just the criteria for failure is changed, so we use the new criteria only. This is the idea.
Yep. It's 490,873.
Yeah, okay. Are you sure? What for?
490,873.85.
Okay, 4,
90
4,
873.8521.
okay. So
Yep.
it is very large value because yeah, the cross section is very big. So
Yep.
okay, but this is the idea if there is no buckling for this problem. Okay.
Yep.
Do you have any other question in buckling?
No.
Okay. So now we finish the first part of our tutorial today. Now we can shift to the second part. Which is torsion. Okay, can you see the screen now?
Yes.
Okay, so now this is the second part of our class today, the torsion. And we have two questions as well for torsion. The first question is we have a rod or a bar, and we have another bar welded to it, perpendicular to it, and we have two applied loads, 50 and 50 Newton, located at 300 millimeter from the the other rod. Okay. The requirement is to determine the maximum shear stresses in the fixed solid 25 millimeter diameter steel shaft shown below. Okay. And if we have a look here, given this is a fixed, this is fixed support, as you can see, mentioned here. Okay. And solid, this means that if we make a cut here, this is a solid cross section. And the diameter for this section is 25 millimeter. Okay. So this is our first problem today. I will shift to the paint to explain in paint. So second part is torsion. The first equation in torsion, you have a shaft fixed in this point, and we have another rod here, or another horizontal member here. We have two forces, 15 Newton here and 15 Newton here. This force is located at 300 millimeter and 300 millimeter here. Okay, we can call this point A. Okay, and again, if we make a cut here, so this cut, this will be the cross section, and the diameter for this cross section is 25 millimeter, and this is a solid section, not a hollow section. Okay, the requirement is to find maximum shear stresses due to torsion in the fixed shaft or the fixed rod. Okay, so the formula for torsion stress or shear stress due to torsion is tau equal to T multiplied by R divided by G. This is the general formula for torsion, where tau is the shear stress due to torsion. So this means that torsion is a type of shear or cause shear stress. Okay, so torsion cause shear stress. What is that? What is T? T is torque or applied torque or torsion moment or twisting moment. All of this is torque. If we have like a shaft or a rod like this, and this is the longitudinal axis of the shaft or the member, so any moment is rotating or applied to rotate around this axis. This means, or this moment is torque or twisting moment, because this moment is causing twist or twisting the element. Okay, and to be more specific, if we have a look on this member, this axis will be z axis, this will be y axis, this is x axis, so this x, y, and this will be z axis. If we draw the plan, this will be x, y, and the perpendicular to this plan will be z. So the moment or the torque is the moment about z axis. Okay, what is R? R is the radius to the point of stress or the stress point. What does this mean? If I have this cross section, circular section, and I want to find the torsion stress at this point A. So from the center or from the centroid of the circle to the point A, this is R. If I want to find the stress at point B here, so this is R1 and so on. So R is the radius to the point of stress. Okay, the last parameter or the last term we need to know is J. What is J? J is the polar moment of inertia. Okay, so this is probability of the cross section, probability of cross section, which resist torsion. So this is the probability of the section that resist torsion. Okay, this J equal to this J equal to pi divided by 32 d to the power 4 for circular. So this for circular section. Okay, where and or we can say that only for solid section. So if the section is solid section, J will be pi divided by 32 d to the power 4. Okay, so this is the 3 parameter needed for this formula. And now if we return back to our problem, this is a fixed part and this is our shaft, and this is the rod here. Okay, and we have two applied load, 15 Newton and 50 Newton. This 300 and this 300. Okay, if we need to apply this formula, T R divided by J. So we need to find this 3 parameter, T. What is the torque moment here? If we have a look in this geometry of the question we have two applied forces, 50 and 50, separated by 600 millimeter or distance. So if we have two forces equal in magnitude and reversed in direction or in different direction and separated by distance, so these two forces will cause a couple moment or a torque. This torque will be the force multiplied by the distance. So this torque will be 50 Newton multiplied by 600. So the torque T will be 50. One of the forces multiplied by the distance between the two forces is 600 millimeters. So that gives us 30,000 Newton millimeter torque. Or we need to find the maximum stress. What is the maximum stress? If we have a look in this equation, R is related to R is proportionally related to tau is proportionally related to R. So if R increase, tau increase. So tau max will be at R maximum. So where to find the stresses? If this our section, cross section. So
Radius.
R will be the radius. Any point on the perimeter will give us the maximum stresses, and R will be the radius. Okay, so R will be 25 divided by 2, give us 12.5 millimeter. Okay, so now we know T and R. The third parameter we need to know is J. J will be pi divided by 32 multiplied by d to the power 4. So pi 32 multiplied by 50, or sorry, 25 to the power 4 give us that J is 38349 millimeter to the power 4. So now finally we can find tau. Tau will be T, which is 330,000 Newton millimeter multiplied by R, which is 12.5 millimeter, divided by J, which is 38,349 millimeter to the power 4. This gives us that tau will be 9.778 Newton per millimeter square. Okay. Do you have any question for this problem?
No,
Just a
just
straightforward, yeah.
just want to confirm the J, which is polar moment. So it's different for every different section.
Yeah. This is just for the circular
So if
circular section.
if it's hollow, then we need to subtract
Yeah. I
the
will.
inner
Yeah.
column.
Yeah. I will. The next problem will be hollow section. Okay. So now we
Oh,
shift to the
great.
second. Yeah. Shift to the second question. You can see the problem now.
Yep.
Okay. So now the second problem we have is also straightforward example, but for a hollow section, not for a solid section. Okay. Here we need to find again the shear stress due to torsion at point 8. Sorry. And point B. Okay. Due to applied torque of 12 kilonewton meter. So we have an applied torque T equal to 12 kilonewton meter. Okay. So this is same idea. Just we have 2 points to find the stress, one on the outer parameter and one on the inner parameter. Okay. So now shift to bend. For question 2, we have 2 sorry. Okay. They are not symmetric, but it's okay. Okay, so we have hollow section in this problem. The outer diameter is given 86 millimeter. The inner diameter is given 62 millimeter. The requirement is to find the shear stress at point A and at point B if we have a torque moment of T equal to 12 kilonewton per kilonewton meter. Okay, and remember that this is a solid section, a hollow section. Okay, so now just remind you with the problem with the formula tau equal to T multiplied by R divided by J. This is the general formula for tau. So we will need to find tau at A and tau at B. Okay, so given T equal to 12 kilonewton meter. This is the first parameter we need. Second parameter R, we will have R at A and R at B. What is R at A and R at B? R will be the distance from the center of the circle to point A. So this is RA. And from the center to point B. So this is RB. RA will be 86 divided by 2. RB will be 62 divided by 2. This gives us 43 millimeter, and this gives us 31 millimeter. Okay. The last parameter we need to know is J. J here, it is hollow section, so the formula will be pi divided by 32 multiplied by d outer to the power 4 minus d inner to the power 4. Okay. Just if we have a hole or a hollow section, we need to subtract the inertia of the hole from the section. Okay. So J will be pi divided by 32. The outer is 86 to the power 4 minus 62 to the power 4. This gives us J equal to 3.919 to the multiplied by 10 to the power 6 millimeter to the power 4. This is J. And now we can substitute in the formula. So tau at A will be 12. Don't forget to multiply by 10 to the power 6 because this is given in kilonewton meter. So to convert to Newton millimeter, need to multiply 10 to the power 6. Multiplied by RA. RA is equal to 43 divided by J 3.19919 10 to the power 6 give us 131.66 Newton per millimeter square, and tau B will be 12 multiplied by 10 to the power 6 multiplied by 31 divided by 3.1919 10 to the power 6. This gives us tau 2 is 949 Newton per millimeter square, and we should expect that tau at A should be greater than tau at B because RA is greater than RB. Okay. Do you have any problem in this question?
All good.
All good. Thank you.